Hi, I'm Justin Raizes, and I'll be talking to you about our work, Interaction Preserving Compilers for Secure Computation. This is a joint work with Nico Döttling, Vipul Goyal, and Giulio Malavolta. In this work, we're concerned with the problem of secure multi-party computation, where all parties provide a private input, and then they get the output. And the security guarantee we want is no information about the input is revealed except for the output. We are further concerned with the setting where all but one party can be corrupted, and we still want security to hold in this setting. Looking at the communication complexity of the work over the years, Yao's original garbled circuit construction scales with the size of both inputs, as well as the size of the circuit which it's computing. More recently, works have come up with Alice or Bob optimized protocols. These are two-party computation protocols where the communication is fully independent of one party's input. Another advantage of these protocols is they are constant round protocols. Another approach to reducing the communication complexity is to use fully homomorphic encryption. Using this approach, it is possible to actually get communication which is completely independent of both inputs for certain functions. You do have to pay a cost according to the communication of an insecure protocol which computes the function. And using off-the-shelf current tools, you will incur a multiplicative polynomial blow up in terms of the security parameter lambda. Another downside of these approaches is that they add 2 additional rounds to the protocol. In this work, we're concerned with constructing multi-party computation protocols where the communication complexity is independent of the size of the inputs. Lower bounds show that we can't always achieve this, but for a rich class of functions, we can achieve communication complexity which is lower than both inputs. As an example, let's consider combinatorial games. If we were, say, to compare 2 different chess AIs, it would be very cost intensive to simply communicate the AIs because they might be very large. However, playing chess only requires the next move to be communicated. Another example of a function which can be computed in much less communication than the size of the inputs is Yao's millionaire problem. And in this problem, 2 parties or 2 millionaires want to figure out who has the higher salary, but they don't want to reveal their exact salary. We're going to consider the insecure version of this protocol for a moment, where the parties don't care if their salaries are revealed. The naive solution to this is to simply send your salary to the other party, and they can do the computation. However, this is linear in at least one party's input size. Randomized algorithms, however, can do communication complexity and rounds which are logarithmic in the input size. And there are more examples of such functions from the communication complexity literature. In this work, we consider the problem of taking an n-round insecure protocol for a functionality f and designing a secure protocol for f with roughly the same communication complexity, both in terms of the number of bits exchanged and the number of rounds. This result will allow us to lift results from communication complexity literature directly into the secure computation setting. We're going to start off by considering the case of security against semi-honest adversaries, which will follow the protocol and try to learn extra information by examining the messages. And we're going to do this in the common reference string model, where the parties all start with a reference string which is sampled by a trusted party and known by all parties. Assuming the hardness of the circular learning with errors problem, we can achieve this. We do have a communication overhead of little of 1 times the worst case communication complexity of the insecure protocol, but asymptotically, this is simply going to be an additive overhead rather than a multiplicative overhead as we saw previously. We do have some polynomial dependence on the last message, the depth of the output circuit, and the size of the output, as well as the security parameter lambda. However, previous work has shown that overcoming this dependency will require some form of program obfuscation. For the case of 2 parties, we get a perfect round-preserving compiler, which takes n-round protocols onto n-round protocols. But for the case of m parties, we do need to add an extra round. However, making the additional assumptions of extractable witness encryption and succinct non-interactive arguments of knowledge, we can get a perfect round-preserving compiler for the more general case of m parties. We do incur a slight increase in the communication overhead. You'll notice that the polynomial term on the last line now has an m in it, which is the number of parties. Given these results, a natural next question is whether or not we can get security against malicious adversaries, which might, they can act arbitrarily and don't have to follow the protocol at all. And we want this in the plain model where we don't have a common reference string. Assuming simulation extractable snarks, in addition to the previous assumptions, we can lift both of our results into this setting at only the cost of adding a polynomial blowup to the second message of the protocol. And we do have a minimum round requirement of 4 here due to some lower bounds on MPC, which needs to be secure against malicious adversaries in the plain model. At the heart of our communication complexity improvements is some results for multi-key linearly or fully homomorphic encryption. Assuming the hardness of learning with errors, there exists a ciphertext rate 1 multi-key linearly homomorphic encryption scheme. If we make an additional circularity assumption, we can turn this into a rate 1 multi-key fully homomorphic encryption scheme. And a multi-key fully homomorphic encryption scheme will allow each party to select its own key. Then any ciphertexts under any of those keys can be computed on under all of the keys. Rate 1 is important because asymptotically, if we encrypt a message, the resulting ciphertext will be roughly the same size. As a starting point, let's consider a basic MPC protocol which uses multi-key fully homomorphic encryption. In the first round, each of the parties will sample a public key, and they will broadcast this along with the first message of the insecure protocol, which is encrypted under those keys. In the subsequent rounds from 2 to n, they will complete the insecure protocol using or underneath the hood of the fully homomorphic encryption. And in round n+1, using the encrypted transcript that they've just computed, they will compute their encrypted outputs. Finally, in round n+2, each of the parties will partially decrypt the outputs from the other parties. And once this is done, they can locally recombine these partially decrypted outputs in order to recover their own output. There are a few improvements that we can make to this basic construction. First, we can shave off 1 or 2 rounds using secure computation tools. We do need to be careful not to increase the communication too much with round reductions, because typically round reduction tools do increase the communication. However, we are able to do this with just a small overhead. The second improvement that we can make is to use a new rate 1 multi-key fully homomorphic encryption scheme. As mentioned previously, current solutions for multi-key fully homomorphic encryption will incur a multiplicative polynomial blowup in lambda, and our new rate 1 multi-key fully homomorphic encryption will asymptotically be just an additive overhead rather than a multiplicative overhead. Let's start by discussing the round reduction. The first tool we're going to use is Laconic function evaluation, which was introduced by Kwok, Wee, and Wicks. In Laconic function evaluation, the right party will compress a large circuit into a small hash, which it then sends to the left party. Using this hash, the left party can then encode their input X and send this back to the right party. Then, given this encoded input, the right party can decode the output of the circuit on that input, but learns nothing else about the left party's input. To see where this will be useful for round reduction, let's consider the last 2 rounds of our basic protocol. As a reminder, in the last 2 rounds, the parties are going to compute their encrypted output and then partially decrypt the other party's outputs. So the LFE circuit that we're going to encode is going to have hardwired into it the transcript until round n-1. This is all that is known when you're constructing your messages for round n, since we have not yet received the round n messages. As inputs, the circuit will take in the last round messages, as well as the secret key of the party which received the LFE hash. Internally, it's going to compute the LFE hash sender's input or output, and then it's going to partially decrypt with the receiver's secret key. And that's going to be exactly the output of the circuit, the sender's output, which is partially decrypted by the receiver. Then we can send this hash in round n alongside the last set of messages for the encrypted insecure protocol. And in round n+1, the parties can then use the hashes that they received in the previous round to encode their inputs. Given these encoded inputs, the parties can then decode the output of the circuit, which is precisely the result of the last 2 rounds in the basic protocol. In the case of 2 parties, we can shave off an additional round by anticipating the messages a little bit better. So instead of sending the messages in round n, we're going to send the Laconic function evaluation hashes in round n-1. Of course, up till this point, we only know the transcript until round n-2. And this slide is from party 1's perspective, so party 1 will also know its round n-1 message because it can compute that from the transcript up till this point. This will also be hardwired into the transcript, or into the circuit. Then after receiving the hashed circuit, party 2 will input its message n-1, which it just sent. It will compute and input its last round message n, and then it will also input its secret key. Internally, the circuit will compute party 1's message n in order to complete the overall transcript, then use this transcript to compute party 1's output and partially decrypt the output with party 2's secret key. It'll then output party 1's output, which is partially decrypted by party 2. And at this point, party 1 can finish decrypting, or finish the previous protocol. It's worth noting that we can't do a similar transformation for the multi-party case because this crucially relies on the fact that party 2 can anticipate its own messages. However, if we were to try and do this in the multi-party case, party 2 would need to know the round n messages for all the other parties, not just itself and party 1. In order to get a perfect round preserving compiler for M parties, we're going to have to turn to obfuscation. So the obfuscated circuit that we're going to use is going to allow the LFE hash sender to compute the LFE input themselves, non-interactively. So hardwired, we're going to have the party's secret key, and the input is simply going to be an LFE hash, which you've received from a different party, as well as the round N messages. Then the output is simply going to be the encoded LFE input for that hash. And as a reminder, the input for the LFE consists of your secret key as well as the last round messages. So we can then send the obfuscated circuit at the same time as the LFE hash, and this saves a round. So given the obfuscated circuit, you can then compute the other party's input to your LFE locally and then decode everything. However, there's a problem with this construction. An adversary, even a semi-honest adversary, can now evaluate the obfuscated circuit multiple times using different nth messages and use this to learn about your inputs. To solve this, we're going to add a commitment, a succinct commitment to your input in a previous round, say n-1, and then in round n, you'll prove succinctly that the nth message is consistent with the committed input. The obfuscated circuit will take in this succinct proof and only evaluate itself if the proof is accepting. Well, I'll note that we can't directly put the witness into the obfuscated circuit since the witness includes the committed input, and that committed input might be very large. There's an additional complication with using snarks. Since they only computationally fix inputs, we can't actually use indistinguishability obfuscation. Instead, we're going to use a token-based obfuscation approach, which consists of a garbled circuit and witness encryption. The witness encryption is going to encrypt the various labels for the garbled circuit so that the evaluator can retrieve just the labels that they need for their last message. And to do this, they can use a snark which proves that their nth message was computed according to the committed input. Once they input this snark to the appropriate witness encryption ciphertext, they can decrypt it to get the garbled circuit labels for that nth message, and then they can use those labels to evaluate the garbled circuit. The security guarantee we get from the witness encryption is any labels corresponding to nth messages which don't have a proof can't be opened. We do need to be a little careful though, because witness encryption only provides security for false statements. Since snarks and the succinct commitment can only bind the input computationally, it could be the case that two different nth messages can be proved. And if this is the case, then the adversary could acquire two sets of labels, which would break the security of the garbled circuit. In order to solve this, we're going to need to use some extractability assumptions, and specifically the existence of extractable witness encryption. Using this, the argument that the adversary can't open two different garbled circuit labels is roughly as follows. Assuming that they could, then they have to know snarks proving that each of those nth messages were consistent with the input. This is due to the extractability of the witness encryption. Then, in turn, the snark argument of knowledge property means that the adversary must know the witnesses which show that the nth messages were consistent with the input. This witness includes an opening to the commitment, so the adversary must know two different openings to the commitment. We'll note that the input here includes the randomness, so this is what the adversary is committing to, both the input and the randomness used in the protocol, and that fully determines the last message. So if they do open up garbled circuit labels which correspond to two different last messages, then they do know the openings to two different committed input and randomness sets. Moving on to the plain model, we previously needed the common reference string for the multi-key fully homomorphic encryption, our rate 1 construction. We also needed it for the Laconic function evaluation, and in the perfect round preserving compiler for multiple parties, we needed it for the snarks. In the semi-honest setting, we can actually just set any party to sample the CRS in the first round. Then, once we have that CRS, we can sample our keys for the rate 1 multi-key fully homomorphic encryption, and then in round 2. And then in round 3, we can key swap into the rate 1 multi-key fully homomorphic encryption. Up until that point, though, we need to use some different encryption schemes. In the first round, we can just use a symmetric encryption scheme, which has rate 1 to encrypt our first message. However, in order to transform this into the second message, we need to key swap into a plain model multi-key FHE scheme, which might have low rate. And the key swapping is simply done by encrypting the symmetric ciphertext underneath the plain model MKFHE, and then running the decryption circuit using the encrypted secret key for the symmetric scheme. We do incur a polynomial blowup in the second message due to the use of the plain model MKFHE, but we don't incur any other blowups in terms of any of the other messages. Moving towards malicious security, let's consider the case of semi-malicious security, where the parties still have to follow the protocol, but they're allowed to choose their inputs in randomness on the fly in order to try and gain information. What we're going to do here is we're going to divide the protocol into two pieces. We'll have the pieces of the protocol which don't require a CRS, and the pieces of the protocol which do. It turns out we can actually replace the CRS for the rate 1 MKFHE with a distributed setup procedure which just takes one round. We adapt that distributed setup procedure from Berkursky et al., and it has security against even malicious adversaries. Then, for the rest of the components which need a CRS, these are only needed later in the protocol. So we can just use a generic 2-round semi-malicious MPC without increasing the number of rounds. This slide only shows the construction for the round n+1 compiler, but similar ideas hold for the round n compiler. Moving to fully malicious adversaries, which can deviate from the protocol arbitrarily, it's well known that we can make any semi-maliciously secure MPC into a maliciously secure MPC using universally composable, non-interactive zero-knowledge. However, we do need succinctness, so we're going to need to use snarks. And simulation extractable snarks are good enough. We don't need full universal composability. However, snarks do need a CRS of their own, and this would blow up the CRS generation protocol to 4 rounds if we used a maliciously secure solution. Since we need the CRS for the snarks and the LFE by round n, we can only compile insecure protocols which already start with 5 or more rounds. And this would give us a total of 6 rounds for the compiled protocol. This is not terribly satisfying, since 4 rounds is optimal for malicious secure MPC in the plain model using a black box simulator. To solve this, our observation is that we can actually use the CRS early as long as it's not revealed publicly. What we're going to do is we're going to go back to using the 2-round semi-malicious CRS generation protocol, and then we're going to wrap everything involving the CRS in a plain model MKFHE, which uses new keys. It's perfectly fine for this plain model MKFHE to have a low rate because everything that involved the CRS already had a multiplicative polynomial in lambda blowup. Then, once we've received a proof of semi-malicious behavior in the CRS generation, we can decrypt the portions of the transcript involving the CRS, and this will provide security because we know that we have security against semi-malicious behavior in the CRS generation. Of course, since such a proof would already take 4 rounds, and we need an extra round to decrypt, we are instead going to use a conditional disclosure of secrets to reveal the key for the CRS portion of the transcript. And once all the parties prove that they behaved semi-maliciously, the conditional disclosure of secrets will reveal the secret key for the CRS portion of the transcript immediately. So that'll happen in the last 4 rounds. And at the end of that, all the parties will be able to decrypt the CRS portion of the transcript and then finish decoding the transcript. Now that we've discussed our round reduction tricks, let's move to our other result, which is the construction of a rate 1 multi-key fully homomorphic encryption. For this, we're going to follow a paradigm for rate 1 fully homomorphic encryption, which was introduced by Brzezinski et al., as well as Gentry and Halevi. We're going to apply it to the multi-key setting, though. The paradigm uses 2 tools. The first is a rate 1 multi-key linearly fully homomorphic encryption scheme. And the second is a multi-key fully homomorphic encryption scheme with a linear decryption procedure. The fully homomorphic encryption scheme is allowed to have arbitrarily low rate. The idea here is normal encryption under this scheme will simply be to encrypt your message underneath the fully homomorphic encryption. This is going to be result in a large ciphertext. Then we can compress that large ciphertext by key swapping into the multi-key linearly homomorphic encryption scheme. We can do this because it allows linear evaluations of linear functions, and the fully homomorphic encryption scheme has a linear decryption process. You'll note that once we have compressed the ciphertext, we can only do linear evaluations on it. In order to get back fully homomorphic evaluations, we can make an additional circularity assumption that allows us to safely add the encrypted linear secret key to the public key. Then using this, whenever we want to evaluate a nonlinear function on a compressed ciphertext, we can simply key swap back into the fully homomorphic encryption scheme, evaluate the nonlinear function, and then recompress. I'll note that multi-key fully homomorphic encryption with linear decryption is already known. Our main technical contribution here is the construction of a rate 1 multi-key linearly homomorphic encryption. To construct this, we're going to extend regev's scheme to pack arbitrarily many messages into a single ciphertext, as well as support multi-key evaluations of linear functions. The message space is going to be eta elements of ZQ, where Q is an even integer. The secret key will be a random eta by n matrix, where n is a parameter which is chosen both for security and for efficiency. The public key will consist of 2 components. The first will be a randomly chosen matrix of dimension n by m, where m is similarly to n, a parameter which is chosen both for efficiency and security. And the second component of the public key is going to be s times a plus some error matrix e. To encrypt something under the public key, we'll have 2 components to the ciphertext. First, we'll have a times r, where r is a random length m bit string. And then the second component will be b times r plus little omega times the vector of messages. And here, little omega is a constant, which is typically q divided by 2. To decrypt, we're going to round the second component minus the s times the first component to the nearest multiple of little omega. For the linear homomorphisms, there are two pieces. First, we need to get an additive homomorphism between two different ciphertexts which are encrypted with the same key, or with different keys. And our observation here is if we keep the first component of each of the ciphertexts, we can combine the second component. Then decryption will simply be to take that combined second component and subtract the respective first components minus their respective secret keys, similarly to the regular decryption process. The second piece of achieving linear homomorphism is to allow multiplication by constants. Of course, multiplying by a large constant could saturate the noise of the ciphertext, which would prevent us from decrypting correctly. The standard trick to resolve this is to use a bitwise representation of the messages being encrypted, and this will ensure that the, multiplying by a large constant doesn't saturate the noise, since we're able to multiply just the particular components and scale everything. In order to achieve rate 1, we do need to add a few more things. First, you'll probably notice that the evaluated ciphertexts scale with the number of keys which are involved. However, we can amortize this out by computing on larger message spaces. This is particularly effective when we're considering compiling insecure protocols which scale in message size with the number of parties involved. The second piece of the puzzle is to use a ciphertext compression algorithm from Brzezinski et al. And this is going to compress multi-key linearly homomorphic encryption or ciphertexts by making use of the fact that the modulus Q is even, as well as the multi-key linearly homomorphic encryption decryption procedure is also linear. You should see their paper for more details. Then, using these two observations, we can make some careful parameter choices to maximize their effect in order to finally achieve rate 1. If you found the talk interesting and want to learn more, please check out the full version of our paper.